Hello everyone, welcome to this video. In this video we'll be answering this question that how many subgroups does a finite cyclic group has, right? So until now we were studying about finite cyclic group. We saw various properties of these groups, about the order, about the groups which are generated by the elements of these group and so on. So now we are talking about the subgroup of this group. So we have a result which is given by this fundamental theorem of cyclic groups. It states that a subgroup, in fact every subgroup of a cyclic group is cyclic in nature. This is one thing that the result here tell us. Another thing that the result tell us here is, if the order of the subgroup which is generated by the element A of this group has order n, right, in that case the order of any subgroup of this element of this group which is generated by this element A is a divisor of n. So that means if the group having order, the group which is generated by A has the order n, then any subgroup of this group would have an order which is the divisor of the order of this group, right? And for each positive divisor, suppose K is that positive divisor, right, then this group would have exactly one subgroup of this particular order, and that subgroup is denoted by this thing. It is obtained by taking an element A raised to power the order of the group itself divided by its divisor, and when we use this to generate the group, that group is the given subgroup of the group, correct? Okay, so to understand this result here, let's move forward and see this example. So in this example here, if G is the group which we are calling a cyclic group and it is generated by the element A here, then we are assuming that the order of group this group is 30. Then according to the first part of the theorem, all the cyclic groups, they would be cyclic in nature, and by the second part, this n, all the divisors of n would form a subgroup of this group, right? So from the first and second part of this theorem, if H is any subgroup of the group G, then this H has a form like this, where it is generated by some element A raised to power 30 divided by K, where K is the divisor of 30, and 30 is what? It is the order of the given group. And the last part, it tells us that we have unique subgroup of such kind. So one subgroup of each of the orders. So we can list all the divisors of 30. They are 1, 2, 3, 5, 6, 10, 15 and 30. So we would have one subgroup each having order 1, 2, 3, 5, 6, 10, 15 and 30. Right? So there would not be any subgroup having order other than those which are listed above. So we would have in total 1, 2, 3, 4, 5, 6, 7, 8 subgroups in total. So let's see what are these subgroups. The subgroups, they are obtained when we have the order 30. Right, when the value of K is equal to 30 here, so your subgroup would be of the form 30 divided by K, A raised to power 30 divided by K, so A raised to power 1. So the subgroup would be that which is generated by A raised to power 1. So it would be E. The next element, E is basically A raised to power 0, right? Next element is A raised to power 1, then next is A raised to power 2 and so on. How we obtain all of them? We just keep on multiplying A and we have all the elements, right? Because here A is the generator. For the next element, we would multiply it 5 times and so on. So we will have all the elements and its order would be 30 because there are in total 30 elements. The next one would be of order 15. Here the element, the group is generated by A raised to power 30 divided by 15, right? And what is this? This is A square. So you can list all the elements like this. It is identity, then it is A square, then it is A raised to power 4 and so on. Why? Because the first element is A raised to power 0 only, the second one is A square, the third one is A square into A square, the fourth one would be A square into A square into A square, and so on. We keep on doing like this until we reach the last possible entry of this group, right? So similarly we have for order 10, the element would be a raised to power 30 by 10, so it would be a raised to power 3. So we are using this to form the subgroup, and the entries would be e, then a cube, then a raised to power 6, then a raised to power 9, and so on. We'll keep on until we reach the element a raised to power 27. For the next element here we have order 6, and for order 6 we have a 30 divided by 6, which is a raised to power 5. So we'll be having a subgroup which is generated by a raised to power 5, and the elements of this group would be e, a raised to power 5, a raised to power 10, a raised to power 15, 20 and 25, and if you count them they are 6 in number, so therefore the order here is 6. Similarly for order 5 we have a raised to power 6 generating the subgroup, and the entries are listed like this. So in total we have 5 entries here. Similarly for order 3, the generator would be a to the power 10, so we have e, a to the power 10, a to the power 20 as its elements. For order 2 we have a to the power 15 as the generator, so we have the elements listed as e, a raised to power 15, right? And for order 1 we have a raised to power 30 as its generator, so we only have identity e as its element, right? So in short, we can also say that the subgroups of the cyclic group generated by A, they are precisely of this form, right? Where what is this m, a raised to power m is the divisor of 30, right? And moreover, if m is the divisor of 30, then that subgroup having order m would have elements of this form, right? So I have illustrated to you that how this thing is there. Okay. So lastly, we could make this statement that if we have a cyclic group, suppose it is generated by A and having order n, and say m divides this n, then subgroup a raised to power n by m would be the unique subgroup of order m, right? So I hope you understood this result. Well, that is it for this video. Thank you for watching.